In the government's latest response,
you must stay at home.
Master of the house, doling out the charm.
It's very important that everyone
know that you are not alone.
G'day. So, what we're about to see is a video that was produced by one of my students for her depth study. I've got both her permission and her parents' permission to share this. It was produced as her depth study, and the reason I'm sharing it here is because, quite frankly, it's outstanding, and it's one of the videos which I'm going to use with my classes moving forward, as both an artifact of student work, but also an explanatory video. So she's done it by animating it in OneNote, and then screencasting that, which is really fairly interesting. It's the reasons that it's so great are, one, the content is outstanding. It's just phenomenal. Two, and just as much, is that the tone of the piece is outstanding. Like it's got humor. It's got some humor, which was definitely directed at me. It's got some, broader stuff. It explains it in a way that is very simple to understand, but doesn't dumb down the content, which I find really impressive. Anyway, so this was made by one of our students, and I just wanted to share it because I thought it was great. So it was made as part of a depth study. So in the New South Wales syllabus for the Year 11 and Year 12 chemistry depth study, or chemistry, we do a depth study where a student has to go far beyond the syllabus and dive into and show that they understand something at a really, really deep level. And that's exactly what our student has done here. Her name's in it, but sort of blink and you miss it kind of thing. Anyway, this obviously got outstanding marks. But again, it got outstanding marks in both the presentation, as in what she's produced, content-wise, and also a part of our marks are what you produce for the audience. So not everyone did a video. In fact, it wasn't necessary at all. Some people made a textbook style thing. Others went all sorts of roads. We had one kid build a game that explained to you how batteries work, and that was really exciting, a video game. So yeah, it was basically, they had to delve into galvanic cells and, the benefits and whatnot, how they work. And this is what our students done. It's really fantastic work. I hope you enjoy it. And yeah, see you next time. Bye now.
Have you ever wondered what starts your car? Or for that matter, how a basic battery works? Our modern society is dependent on batteries. They are in many home essentials like torches and TV remotes. Our phones and laptops run off them, and our cars are started from their stored power. This video will be in 3 parts: redox reactions, classic galvanic cells, and lead-acid batteries. Galvanic cells use spontaneous redox reactions to create electricity. A redox reaction is a reaction where one participant loses electrons, or oxidizes, and the other gains them, reduces. It occurs when 2 participants with different electronegativities meet. Electronegativity is the tendency of an element to attract electrons, and it increases left and up the periodic table. The most electronegative elements include fluorine, oxygen, and chlorine. The differences in electronegativity encourages the 2 participants to spontaneously begin exchanging electrons. Electrons are exchanged because the 2 participants want to achieve a full valence shell of electrons. This makes them ions, or charged atoms, and it is a more comfortable, low-energy state to exist in. A spontaneous redox reaction converts the chemical potential energy in the participant bonds into heat or kinetic energy. Oxidation is the loss of electrons, and is experienced by the participant with a lower electronegativity, which is more willing to ionize. The higher electronegativity of the other participant means it's unwilling to lose its electrons, but is eager to attract others and reduce. The gain of electrons is known as reduction. Each participant is also an agent, causing the other to experience either reduction or oxidation. If it causes oxidation, meaning it itself is experiencing reduction, it is known as the oxidizing agent, or simply the oxidant. If it causes reduction, it is the reducing agent, or the reductant. This is all a little bit confusing, so I will include an example that is important later in the video. An example of a redox reaction occurs between zinc and copper when a solid zinc strip is placed in a copper solution. But wait, hold on. Why do two metals react together? Well, metals have varying reactivities based upon their electron configuration and atomic radius. These reactivities are recorded in an order known as the metal activity series, and that relates to metallic electronegativity. An atom that is high on the metal activity series has a lower electronegativity, meaning it is more reactive and likely to lose electrons. Very reactive metals include lithium, potassium, and calcium, and they all want to oxidize to get rid of their pesky valence electrons. Metals that are more willing to lose their electrons are far more reactive than others, like gold, which is very unreactive. The difference in reactivity and electronegativity causes metals to experience redox reactions, where a very reactive metal will oxidize. This means the more reactive metal is always the reductant, making another metal gain its electrons. Zinc is more reactive than copper, so it is the reductant, meaning it experiences oxidation and loses electrons. Copper will reduce and gains the electrons zinc loses. One last vital point about metal activity. A more reactive metal always displaces the ion of a less reactive metal from a solution. So, let's set the scene. A zinc strip submerged in copper solution. The former is more reactive and surrounded by copper ions. What could happen? Well, the zinc atoms and copper ions will effectively switch places. The solid zinc atoms give copper ions their electrons, and then they go gratefully into the solution. When the reaction is complete, the solution will be mostly zinc cations, and a copper deposit will have formed on the zinc strip. The redox reaction will continue until the reductant is exhausted and has no more neutral atoms to oxidize. Redox reactions are represented with half equations, which examine both what the individual participants experience and the electron movement between them. Half equations must have balanced atoms and charge. For the zinc plus copper reaction, the two half equations are solid zinc becomes zinc cation plus 2 electrons, and copper cation plus 2 electrons becomes copper solid. So, what is a galvanic cell? Classic galvanic cells are basic batteries developed upon the voltaic pile invented in 1800 by the Italian scientist Alessandro Volta. As I said earlier, galvanic cells use spontaneous redox reactions to convert chemical energy into electrical energy. A classic galvanic cell separates the oxidation and reduction parts of a redox reaction into two half cells. Each half cell contains a conductive electrode and electrolyte, and they are connected externally by a circuit and internally by a salt bridge. An electrode is an electrical conductor that is the site of either oxidation or reduction, and an electrolyte is a neutrally charged solution. Electrodes are either positive or negative. The more reactive metal, which is always the reductant, is the positive electrode called the anode, as it is losing electrons. The anode is the site of oxidation. The negative electrode is called the cathode, and it is the site of reduction. In a classic galvanic cell, the electrodes are two metals, usually zinc and copper. The zinc strip is the anode, and the copper strip is the cathode, and they are submerged in solutions, zinc sulfate and copper sulfate respectively. When connected by a circuit, a redox reaction will begin between the two half cells. This reaction involves the oxidation of the zinc strip and the reduction of the copper solution. The zinc strip is composed of many neutrally charged zinc atoms. When the reaction begins, zinc atoms in the anode ionize, expelling electrons through the circuit. A single zinc atom will push 2 electrons into the circuit and become a cation with a +2 charge. This cation disconnects from the solid and enters the aqueous solution. The electrons travel through the circuit, connecting the two metals, and then flow down through the copper strip. The positively charged ions in the copper solution gain the electrons and they become neutrally charged. They then move from the aqueous solution onto the copper strip as a solid deposit. This transfer occurs because of differences in energy states. Energy states are complicated quantum mechanical concepts, but they refer to the placement of electrons around a nucleus and the excitement or energy this gives them. When the electrons are with zinc, they are more excited and want to move around and react with things. However, energy states are tiring and electrons like to avoid them. They are less excited with the copper, more relaxed, so the reaction will transfer them from high to low energy via the circuit. The redox reaction process means that a buildup of charge occurs in both aqueous solutions. In the zinc sulfate solution, there is a significant increase in positive charge as zinc ions go into solution, overwhelming the negative sulfate ions. In the copper sulfate solution, the opposite occurs, with copper ions removed from solution, leaving an abundance of sulfate ions. The salt bridge is what evens out these charges. The salt bridge contains a neutral solution of cations and anions, a common example being potassium chloride. At each end of the salt bridge, where it interacts with the two metal solutions, a semi-permeable membrane stops all the solution rushing out of the bridge. The negative charge from the copper solution draws the potassium cations through the membrane, and the positive charge of the zinc solution attracts the chloride anions. This means that charge doesn't build up in the solution and hinder the reaction. To predict the reaction that will occur between two half cells, chemists compare their reduction potentials. Standard reduction potential is a measure of a half cell's tendency to reduce or gain electrons in a reaction under standard conditions. Standard conditions refer to pressure, concentration, and temperature. Under non-standard conditions, reduction potential of half cells will decrease. Reduction potential can be positive or negative, and it is measured by connecting a half cell to a standard hydrogen half cell, which is a hydrogen half cell with a reduction potential of 0 volts. The half cell with a high standard reduction potential will be the oxidant, experiencing reduction, while the half cell with a lower reduction potential will be the reductant. For example, copper in an aqueous solution plus 2 electrons has a reduction potential of 0.34, while zinc in solution plus 2 electrons has a reduction potential of minus 0.76. This means in a galvanic cell with zinc and copper, the copper is the oxidant and zinc is the reductant. Reduction potentials are also used to calculate a cell's voltage or potential. Chemists rank elements on their electrical potential in a table of standard reduction potentials. Electrons flow through a circuit because one half cell has a greater tendency to oxidize and push electrons than the other half cell. The difference in this tendency is called potential difference or electromotive force. The measure of this potential difference is called cell potential or voltage and is represented with the symbol E cell. Standard cell potential is found by subtracting the anode reduction potential from the cathode reduction potential. A reaction will produce the most free cell potential if there is a great difference in reduction potentials. Cell potential is also used to test if a redox reaction will occur spontaneously. If standard cell potential is negative, meaning the two reduction potentials add together are less than 0, then the reaction will not occur spontaneously. Zinc and copper have the reduction potentials of minus 0.76 and 0.34 volts respectively. To find the standard cell potential of this classic galvanic cell, E cell equals 0.34 minus 0.76, or 0.34 plus 0.76, which is 1.1 volts. This means that a galvanic cell of zinc and copper will produce a maximum of 1.1 volts. So, what are the uses of classic galvanic cells? Well, there are two types of electrical current. Direct current, DC, contains electrons flowing in only one direction, while the electrons in alternating current change direction. Classic galvanic cells are used as a source of DC electricity as the electrons only flow in one direction. Classic galvanic cells, which use a salt bridge to connect the solution, are not really used today, but the developments made with classic galvanic cells have led to great innovations in electrical storage. The chemistry behind classic galvanic cells has been used to create new batteries, like dry cell batteries found in many household essentials, and also to develop rechargeable batteries like lithium-ion batteries and lead-acid batteries. There are errors that occur in classic galvanic cells. Cell voltage or cell potential will be reduced by an increase in temperature or a decrease in solution concentration, which lowers electron flow. Electrode crust also decreases electron flow as it inhibits contact between the electrodes and the solutions. This can be targeted, however, by cleaning tarnished electrodes. If the salt bridge is not immersed or dries out, then charge will build up in the solutions and inhibit electron flow. the level of electrical resistance and electrode immersion will both decrease cell potential. Classic galvanic cells can only be used once. This is because while the reaction occurs, the anode is slowly degraded until there is no more material to oxidize, terminating the current and voltage and reducing the cell potential to 0. Part 3. Lead-acid batteries. There are differences between lead-acid batteries and a classic galvanic cell. However, the fundamental chemistry that both create power with is the same. In a lead-acid battery, 6 galvanic cells containing a lead and lead dioxide plates are submerged in dilute sulfuric acid. Lead-acid batteries are cheap and rechargeable, while offering high voltage, making them very desirable in the modern society. They do have their disadvantages though, including environmental unfriendliness, low charge efficiency, and their weight and size. A single cell in a lead-acid battery contains 2 strips submerged in dilute sulfuric acid. These strips are made of lead and lead dioxide. The reaction that occurs inside a single cell of a lead-acid battery is a redox reaction. However, it is a little bit more complicated than in this classic cell. The electrolyte of a lead-acid battery is a solution of around 63% water and 37% sulfuric acid. The charged hydrogen and sulfate ions of the sulfuric acid are interspersed through the electrolyte. The state of metals is important here, not because of their conductivity, but their reactivity. Metal solids exist as a lattice structure where metal cations are surrounded by a sea of delocalized electrons, meaning they are not bonded to a specific atom. In the lead strip, the metal cations have a charge of 2+, while the sulfate anions in solution have a charge of 2-. The electromagnetic force between these opposing charges and their desire to achieve stability causes an oxidation reaction to occur. The sulfate gives the lead the 2 electrons it was carrying and bonds to a lead cation, creating a precipitate of lead sulfate that collects on the lead surface. The lead strip is the anode because it is the site of oxidation, where sulfate loses its electrons. At the lead dioxide cathode, the reduction reaction occurs between the sulfuric acid in solution and the lead dioxide. Lead dioxide is a structure made when 2 oxygen anions with a 2- charge bond to a lead cation. When the sulfuric acid interacts with the submerged lead dioxide, a reaction occurs that expels 2 oxygen anions, leaving the lead cation behind. The negative charge of the oxygen attracts 2 hydrogen cations, which then bond to form water. 2 water molecules are formed for each process, and the lead strip loses negative charge, causing it to become positive. The lead then reacts with the sulfate ions to form lead sulfate, which forms as precipitate on the strip's surface. The half-cell equation for the lead anode is lead plus sulfate becomes lead sulfate plus 2 electrons. Meanwhile, the lead dioxide strip has a more complex equation. Lead dioxide plus sulfate plus 4 hydrogen plus 2 electrons becomes lead sulfate plus 2 water. The reduction potential of the lead half cell is minus 0.36. Meanwhile, the lead dioxide half cell reduction potential is 1.68 volts. Due to its higher reduction potential, the lead dioxide half cell will be the oxidant experiencing reduction. This means the lead half cell will be the reductant. The cell potential of a single cell in a lead-acid battery is 1.68 minus 0.36, or 2.04 volts. As there are 6 cells in a lead-acid battery, the battery's accumulative cell potential is 12.24 volts. Differences in conditions such as concentration, temperature, and pressure, an average lead-acid battery produces approximately 12 volts of electricity. As the cell potential is greater than 0, this reaction will occur spontaneously. Lead-acid batteries and many other modern batteries are self-contained. They use a single electrolyte which is dispersed through the system, which means a salt bridge and separate containers are not required. While a salt bridge is not needed, lead-acid batteries have a separator that sits between the electrodes. In flooded batteries, where the electrodes are surrounded by acid, this separator is a semi-permeable insulator that optimizes electrical current by inhibiting electron flow through the electrolyte. Sealed lead-acid batteries, or SLA or acid-starved batteries, contain the electrolyte inside the separator as a porous disc or gel. This controls electron and ionic flow and prevents acid being leaked into the battery's environment. Lead-acid batteries can be recharged and used over again. A galvanic cell that can be recharged is called a secondary cell. When it is being recharged, the lead-acid battery is not a galvanic cell and is instead an electrolytic cell. An electrolytic cell is the effective opposite of a galvanic cell, and it turns electrical energy from a power source into chemical energy by driving a non-spontaneous redox reaction. In a lead-acid battery, recharging the battery reverses the reaction that occurred during discharge. This means the electrons are run in opposition to the direction they spontaneously moved in. A power source needs over 2 volts to reverse the spontaneous reaction, as it must effectively outrank the potential of the discharging cell. During recharge, electrons are pushed into the anode, the negatively charged porous lead, reducing the lead sulfate into lead and sulfate ions. At the cathode, the positively charged lead oxide, the lead sulfate is oxidized by the water and forms lead oxide, hydrogen, and sulfate ions. The two half-cell equations are the opposite of their galvanic counterparts. At the anode, lead sulfate plus 2 electrons becomes lead and sulfate. At the cathode, lead sulfate plus 2 water molecules becomes lead dioxide plus sulfate plus 4 hydrogen plus 2 electrons. Lead-acid batteries are cheap, dependable, and very robust with a range of purposes. Starter batteries are designed to deliver high amounts of voltage for a short period of time, thus making them perfect in vehicles for automotive SLI, or starting, lighting, and ignition. Heavier deep cycle batteries have thicker plates than starter batteries and provide continuous power to vehicles like wheelchairs, forklifts, and golf carts that do not have an engine. Deep cycle batteries provide continual power and can cost up to double the price of starter batteries. SLA batteries are usually more expensive than flooded lead-acid batteries. They are used for hospital, healthcare, emergency lighting, and wheelchairs. Other uses for lead-acid batteries include uninterrupted power supplies. Lead-acid batteries have several limitations. Due to their large lead content, they have a low energy density, which relates to the ratio of weight to energy delivered by the battery. Lead-acid batteries also face issues in discharge and overcharge, which limit their uses and cycle count. A battery's efficiency also decreases as it nears the end of its cycles. Lead-acid batteries have different cycle counts, which range from 200 to 1000, depending on the battery type and condition. This number is subject to the treatment the battery receives. Lead-acid batteries should not be fully discharged, subject to overcharge, or subject to high temperatures, as all increase aging, degradation, and electrolyte usage. When discharging at high rates, the battery's voltage has a tendency to plummet, making them unsuitable for high-rate application. Leaving a lead-acid battery discharged also causes sulfation, which is the crystallization of lead sulfate sediment around the electrodes. This reduces battery productivity because reactive metal is decreased and electrode-electrolyte contact is inhibited. Lead-acid batteries should not be stored in a discharged state or be completely discharged to avoid sulfation. Batteries are overcharged to eradicate any sulfate crystals on the electrodes. However, overcharging a battery for too long or too frequently overheats and overcharges the electrolyte and causes the gassing or electrolysis of water into hydrogen and oxygen gas. The accumulation of these gases causes a significant increase in internal pressure and/or the release of hydrogen gas into the battery's environment, possibly creating an explosion. To maintain electrolyte amount and concentration, flooded batteries must be topped up with water. Towards the end of its cycles, a lead-acid battery will inevitably experience shedding, which is another name for the corrosion of lead from the electrode plates. This is a natural phenomenon that will inevitably occur in a lead-acid battery and can only be delayed. The loss of reactive material from the grid occurs when particles of the reactive metals degrade and is shed as sediment. There is no way to completely prevent shedding, however, limiting discharge depth, controlling overcharge, and functioning at a moderate temperature all delay and reduce corrosion. Well, I hope you've learnt more about redox reactions, classic galvanic cells, and lead-acid batteries. Thank you and have a nice day.